Welcome to the final lecture. I'm Chris Garvey. This is an introduction to small angle scattering. In this final lecture, I'm going to talk about techniques which allow small angle scattering to gain information that no other technique can, particularly with application to membrane biology. I will introduce the concept of contrast variation and deuterium labeling. I will talk about molecular dynamics simulations and the complementarity between the two perspectives. I'll make some more general remarks on complementary experimental techniques and how one can improve the information content of small angle scattering experiments, and finally look at these new facilities that are becoming available in Sweden, that is the MAX4 synchrotron and the European spallation source. If you consider the expression for the scattered intensity from a two-phase system, the scattered intensity is proportional to the square of the difference of the SLDs for the two phases, i.e. it's an effective means to increase the scattered intensity. We can use it to simplify a scattering problem which is three phases into two phases by matching the SLD of the two phases, or modulating the intensity of a particular phase. It's also a way of reducing background, and we'll go into that in the practical sessions. There's limited opportunities for contrast variation in small angle X-ray scattering in biological systems. It's much easier for neutrons. If we consider this plot of scattering length density and X-ray scattering amplitude for X-rays and neutrons, the X-rays are the straight line, and you can see that it just goes up uniformly with atomic number. The first thing you can notice about the neutron scattering curve is that it's really quite all over the place. That is to say, the scattering length density is no strong function. But if one considers that biological systems, being made basically of carbon, hydrogen, and oxygen, are all clustered on the bottom left-hand corner, really X-rays are really not so much used. There's not that much contrast and not much that difference between all the atoms in the material. However, you notice that hydrogen and deuterium have really quite different scattering lengths, and this is really a very powerful opportunity for contrast in biological systems. Or to put it another way, if you consider the cartoon on the right-hand side at the top of this slide, in the first cuvette we have what's a three-phase system, little circles in squares in a solution. By matching the squares to the solution, one first of all sees just the circles, and in the third case, if you match the solution to the circles, you only see the squares. And in this way, you're able to concentrate on various aspects of the structure with slightly different experiments. So neutrons allow us to look very differently at matter. They're highly penetrating, they're non-ionizing, they see deuterium very differently from hydrogen. There's an easy implementation, in fact, of contrast variation just by changing the D2O H2O ratio of the solvent. There's less easy implementation of deuteration through chemical or biological deuteration, and I'm going to talk a little bit about that in the next few slides. Let's think very grossly in terms of the composition of biology. It probably is made of water, polysaccharide, some lipid, some DNA, and some protein. On the bottom axis, we have mixtures of H2O, D2O. And so the blue line is the scattering length density of water, and it can be changed continuously by changing the ratio of H2O to D2O. The other lines represent the scattering length density as a function of D2O of different biomacromolecules. They may change slightly because they have different degrees of exchangeability. For example, the lipid line doesn't change very much, but the protein may contain exchangeable hydrogen. But for each of these classes of molecules, you can see there's a point at which the blue line, the light blue line of water, intersects. So, for example, for DNA, this is about 62% D2O. What this means is that this contrast, one can match out this molecule in a complex mixture and concentrate on other structures. This is something you can only do with neutrons. This slide comes from one of the many biodeuteration facilities around the world. It's just schematically how molecules are biodeutrated. So microorganisms are grown in maybe a deuterated carbon source or in D2O, and the bacteria or algal are taught to grow in D2O, and what you end up with deuterated biomass. Then this needs to be purified in terms of the molecule that you're interested in. As there are biodeuteration facilities, there are also chemical deuteration facilities. And the synthetic strategies for deuteration are quite wide and varied. This is just an exchange protocol using a PAR reactor, high pressure and temperature. One ends up with deuterated molecules and one needs to purify them. At the bottom, I've given you a link where there's some resources where you can see where these deuteration facilities are and about the access. Here's a very simple illustration of the power of deuteration from my own work. What we have here is a mixture of a lipid, and in the top left-hand corner we've measured the scattering curves as a function of the ratio D2O-H2O in water. Then we've done the same thing with some glucose. If you look at the right-hand side, we've plotted the square root of the intensity as a function of the H2O-D2O ratio. At the match point, the scattered intensity is 0. And we can determine this from several linear regressions. If we add a little bit of sugar, it shifts the match point due to the perturbation of the sugar to the overall SLD. This method actually allows us to measure how much sugar is in the lipid. This is information that you would not get by any other technique, and is really quite simple. But the contrast term for a two-phase system is just the difference in the square of the difference between the two scattering length densities. The scattering length density is just the summation of a cross-section, the scattering cross-section, for all the atoms in a representative volume of that material. So you can see it's a function of the number or the stoichiometry of the molecule, the individual cross-sections, the density, which relates the molecular formula to the mass, and the sum of the atomic weights. Now, it's quite easy to implement such calculations in a spreadsheet, and this can be quite useful, or there's some web tools for calculating scattering length density for neutrons and X-rays. I've given you an example of the NIST calculator, which is available online, and also there's a link there to a piece of software which will do it for you. The NIST calculation is really based around neutrons. It does do some X-rays for the copper K alpha line of which is quite commonly used in lab X-ray sources, but the online tool will do it for all energies commonly available at synchrotron X-ray beamlines. Molecular dynamics simulations and small angle scattering are really quite a natural pairing when you think about it. Molecular dynamics, for want of a better way of putting it, is really a way of animating the molecular interactions in the context of statistical mechanics and provides a representation of where the system may go. The outputs from molecular dynamics simulations are really quite amenable for comparison with small angle scattering's view on statistical nanostructure. In this sense, both techniques are complementary. Molecular dynamics can provide molecular scale arguments for the nanoscale structural changes which small angle scattering sees, and small angle scattering provides a statistical perspective for the logical outcome of molecular dynamics simulations. And I guess in this sense, I'd really like to say no more, because you could talk a lot about this for an awful long time. I think it's the subject of a whole lecture series. If you're interested further in this topic, there's rather a nice web resource there and a couple of references from the literature. I think this is a rapidly evolving area, and it's just because of the natural pairing between small angle scattering and molecular dynamics simulations. In this lecture series on small angle scattering, I've been, I hope, at pains to point out the limited information content of the small angle scattering experiment. And in this sense, it's very important to supplement the perspective of small angle scattering with other experimental techniques. Now, I've given a few examples here, but really what I'd like you to think about is the limitations of the data and the experiment that you've done, and to think about how one might make the story a little bit convincing. So the first example I've given is fairly obvious: real space, looking down a microscope and actually to see what you have, whether it be a sphere, something elongated, or even more complicated shapes. And probably real space methods are much more effective when looking at the more complicated shapes. The drawback of TM and SEM is that you have to prepare the sample in a special way, and you get a limited statistics on the objects. So the two techniques in this case are really quite complementary. Densitometry, although a very simple measurement, is very useful when you come to do modelling. Quite often, and we've talked about this just recently in this lecture, when one wants to calculate the scattering link density, one needs to know the volume per molecule, or the density of atoms in a particular volume, to calculate the scattering link density. So densitometry is an excellent complement to small angle scattering measurements. The last and the simplest example that I've given is dynamic light scattering. It really gives you very simple information. In the first case, the hydrodynamic radius of particles, which should be slightly larger than the radius of gyration. So it's quite helpful and is an initial constraint in the modelling. But also it's an excellent quality control over sample polydispersity. It's extremely sensitive to polydispersity in a way that small angle scattering isn't. So finally, I'd just like to talk a little bit about the future and the facilities at the ESS and Max 4, with particular reference to small angle scattering equipment. So eventually it's planned to have 3 SANS instruments at the ESS. 2 of these are currently under construction, and in this slide I've just given a broad overview of the intended applications for each. The first one is really offered at soft matter and biophysics. The general purpose SANS is probably more hard matter, and the BioSANS is form factor reconstruction of molecules in solution. So each of these instruments has its characteristics and limitations, and for a particular scientific problem there's one that's better than the other. And as I said before, only the first two are under construction at the moment. Let's have a look at these in a little bit more detail. Loci is an instrument with fixed Q resolution. It's reasonably short, particularly compared to modern day reactor-based sands, but it has quite an impressive Q range in one measurement. That's quite a bit lower and higher than many sands instruments. Skadi is a much longer instrument. It has an adjustable Q resolution. It goes slightly lower in Q than Loci, but one may not even need that. And again, it's designed to cover a large Q range in one shot. In this case, through a bank of detectors. The Cossacks beamline at Max 4 is a variable wavelength pinhole camera on a synchrotron. It can cover quite an impressive Q range and will have many interesting and useful sample environments. In this case, I've just picked out one, which is a robot-controlled sample changer, which is extremely good for doing small angle scattering from solutions and form factor scattering. Here are some pictures just to prove that it's actually more than just under construction, and some scattering pattern off the beamline. So thank you for your time and attention during these lectures. If you have any questions, don't hesitate to contact me via my email, and hopefully this will become all a lot clearer when we do a practical session in about a week's time.